Here's a problem of the day. Go ahead, pause the video and attempt this. So there's infinitely many ways to solve any of these things, but two ways I could see going about doing this. The easy way and the hard way. Let's do the easy way first. One thing to notice right off the bat is that you could get a tangent out of this. So what I'm going to do is say, well, we have a sine and a cosine. If I have sine over cosine, so if I bring the cosine down into the denominator right here, I get a tangent. That just means I need to bring that guy out here. I mean, I could leave him there, then I'd have 1 equals root 3 tangent. I don't want that. I want tangent all by itself. Right here like that. So that I get 1 over root 3 is tan x. Okay? So now I'm trying to solve for x. And so immediately I see 1, I see root 3, and that makes me think of this guy right here. 1, 2, root 3, and I think, okay, tangent is opposite over adjacent, and so I need an opposite over adjacent, so I need this one right here, which is pi over 6. So tangent pi over 6 gives me 1 over square root 3. That's part of the answer, but we are supposed to solve on this interval. That means we need all the solutions on that interval. I think that the best way of doing this is to graph it real quick so we can see if we're going to miss anything. And so I'm going to graph tangent. I know tangent starts here, does this thing. There's pi over 2. Starts here, goes down and does this, comes up like that. That's at 3 pi over 2. Here's pi. Here's 2 pi, it comes up and it goes down. Okay, so 1 over root 3 is a positive number, and it's less than 1, so 1 over root 3 is like that. So I do expect that in this interval I should have 1, 2 answers right there. Okay, and we know obviously the one that's between 0 and pi over 2 is the pi over 6 that we found a second ago. Now we just need to find this. It's something over 6, and it's between pi and 3 pi over 2. Or we could do this with, thinking about, I guess we could call it now polar coordinates. It's a way of thinking about it instead of calling it whatever we called it at the beginning of class. We have a pi over 6 right here. And then we're looking for something in it's going to be the third quadrant, because if that's pi, we're between pi and 3 pi over 2, and so it must be that guy right there. That would be 6 pi over 6, so how about 7 pi over 6? So that's the other answer we're looking for, is 7 pi over 6. So, solving this on this gives me x is either pi over 6 or 7 pi over 6, like that. Another way, if you don't like doing it this way, you could say, well, hold up, tangent is positive. I know that tangent, because that, 1 divided by square root of 3 is a positive number. And you could say, I know that tangent is positive here in quadrant 1 and in quadrant 3, and so on and so forth. That's another way you could reason the same way to get the information that I got by actually graphing it. You can see it means exactly the same thing. You can see that tangent is positive here in the first quadrant. It's negative in the second quadrant. It's positive again here in the third quadrant. And it's negative here in the fourth quadrant. So on and so forth, right? So we get 2 answers. Those are the answers, and we're done. Now, here is the bad way. Don't do it this way. What you could have done is you see sine and cosine, and you think, how are they related? Oh, sine squared and cosine squared, blah, 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 blah. And so you immediately say, okay, I'm going to square both sides. And you do that, so you get cosine squared x equals, square that entire thing. That gives you 3 sine squared x. What are we going to do from here? Well, you're thinking, I don't know about you, but when I see sine and cosine, I'm thinking, okay, how can I get this to give me a 1 somewhere. And you could try to rearrange this, but you're not going to get sine plus cosine anything. And even if you could, you have a 3 in front of the sine. And so, like for instance, cosine squared plus 3 sine squared, that ain't 1, right? You'd have to factor out the 3, but if you factor out the 3 from there, you'd end up with a third there. There's just not a way to do it. So, what could you do? Well, one thing you could do is say, since this is true, then how about we get that cosine squared is equal to 1 minus sine squared, and we substitute it in here. That's probably the way I would think about going forward. 1 minus sine squared x equals 3 sine squared x. Okay, getting closer. That looks good. How about we get all the sines on one side? So that gives me 1 equals 3 of them. I add one more, I get 4 of them. Sine squared x. Okay. Divide by 4 gives me this. Square root both sides, but here's where the problem comes in. Now you're taking the square root of both sides, you get a plus and a minus. So you have plus and minus 1/2 equals sine x. So now you go to solve this. Well, immediately you see 1/2 and you see a sine, and so you go 1, 2, root 3. Sine is opposite over hypotenuse, and so you'd say, okay, then the x, one of the x's should be pi over 6, right? Just like before, which is true. But you're also getting this, and if you really think about what's going on, you're saying that sine x, which you know looks like this, it goes boom, 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 it goes here at pi, here at 2 pi, here's pi over 2, here's 3 pi over 2, here's 1, here's negative 1, and you go, well, if sine is equal to plus or minus 1/2, then I have positive 1/2 up here, and I have negative 1/2 down here. So now we're expecting 4 answers. And so you go through and say, okay, the same kind of analysis. You know it's something over 6 because you've done this thing. So you say, okay, this one should be pi over 6. This one should be, what, 5 pi over 6. This one would be 7 pi over 6. And this last one would be 11 pi over 6. But now you have to stop and go, wait, are all of them true? Well, no, they're not, because we just saw when we did this originally, we got the correct ones that work. So why are we getting these other 4? Where is this guy coming from? Where is this guy coming from? It's kind of strange. How did we end up with all this? Well, you squared both sides of an equation. So you basically, regardless of if, because when we did this earlier, we had positive 1 over root 3 was equal to sine over cosine. And so remember we said, oh, that's wherever, so that is where tangent is positive. But now you've taken that, you've squared it, you got rid of it, you got rid of that information about it being a positive number. If it had been a negative number at the beginning, like if we had started with negative cosine equals root 3 sine, we'd rearrange this, you'd have negative 1 over root 3 equals sine cosine. Then you square both sides, well, you get rid of that negative, and so what usually whenever you square an equation, you pick up answers that may not work. So if you went along this route here, you'd have to check each one of these and see if they work. And indeed, when you plug in this one or this one of these sides is going to be negative, the other one's going to be positive, and that's not going to work out very well for you. And just to be clear, so again, the squaring things, if you can get away with not squaring something, don't square it, okay? Sometimes you have an equation and the only way to go about getting to the answer is squaring this guy. Okay, so be it. Then you have to do your analysis there at the end. But if you can get away with not squaring an equation, don't square the equation, because you're going to you may pick up answers that you don't want. For instance, let's say we had this, x minus 1 equals, let's do 5, okay? Obviously x equals 6. If I need to explain that, we need to go back. But let's say here again, right, we have an equation. Let's just see. So, okay, obviously x is equal to 6, and that's the only solution that's going to work. Plug in a 6 minus 1 equals 5, yes. But what happens if you square both sides? Square, square. Now you have x squared minus 2x plus 1 is equal to 5 squared is 25. Ooh, now you have a quadratic. And so we have x squared minus 2x minus 24 is equal to 0. Okay, so you factor that guy out. And you have your x's here. 24 and 2, how about, what is it, 6 and 4, I think? 4 and 6 should work. 4 and 6. One's plus, one's minus. We need it to be a minus 2, so how about we put the minus there, like that. And so now we get two answers. X is equal to negative 4 or x is equal to 6. Then you'd have to go back to the very beginning and see which one of these work. Well, if you've squared your equation. You can see why this is why both of them work. Plug in your 6. You get 6 minus 1 is 5 squared is indeed equal to 5 squared. Plug in the negative 4. Negative 4 minus 1 squared is negative 5 squared, and because you square it, now the sign doesn't matter. So, see, when you square an equation, you pick up what we call, if you remember, extraneous solutions. They work in the squared equation because you have this thing. This is true, that negative 5 squared is the same thing as 5 squared. But that's not what we're looking for, because our original equation wasn't squared to begin with. So if you tried to plug that in, you'd have negative 4 minus 1 is negative 5, not equal to 5. And so that's what happens if you try to square, when you square an equation, you always have to stop and say, hold up, have I picked up extraneous solutions? In this case you have, and so you have to throw it out. When you're dealing with trigonometric equations, then your life gets much harder, because now, like, you may end up picking up a lot of stuff and then it's very hard to go through and do this. So the point is that if you could get away with not squaring a trig equation, don't square it. Okay? All right. So there's that. Homework. Number 32, page 746. Numbers 29 through 49 odd, and number 61. Okay? That one's a bit difficult. You will need to read the prompt above it. It says, some calculators use an algorithm, blah, 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 blah. I'm going to tell you, I wrote here, use decimals. What I mean is, use a calculator to do this. And what you're going to need to do, what I want to see on your page, is that you write square root of 5 equals, and then use your calculator to get a bunch of decimals here. Okay, so it's going to be 2 point something, I don't know, whatever it is, but write a whole bunch of decimals there. Then do your work, and I said show each xi. What you're doing is you're coming up with a sequence for x. And what I want to see is x1 equals some stuff. Okay, so you've done some work, blah, blah, blah. x1 equals some stuff. If you do some more work, x2 equals some stuff. Each one of these stuffs should be a decimal number, and you're trying to get it until you keep doing this. You keep going until you get to whichever one it happens to be where they match to the first 6 decimal places. And once you get the first 6 decimal places of this match this, then you could stop. Okay, so that's that. Let's begin. Okay, we're talking about summation notation. Summation, meaning a sum. You're adding a bunch of things together. And there's a very nifty way of writing this. And I'm just going to put it up on the board here. So what you're going to see is this thing. That's the Greek letter sigma. It's a capital sigma. Lowercase sigma looks like that. If it shows up at the beginning or the middle of a word, at the end of a word, it looks like this. Anyway, that's neither here nor there. But that's a capital sigma. Now, let's say we had some sequence. A then, right? Blah, blah. And so that's A1, A2, and so on, AN, and so on. what you could do, say, okay, we're going to add up the A sub, in this case, let's call it, how did I want to do it? Say the A K's as K goes from, did I start with 1? I did start with 1. As K goes from 1 up to some number M. What? What does this mean? Well, this means this. This means you're just adding up the AKs and you're starting here with 1. So the K is 1. Then you add that to when the K is 2. And then you add that to, and you keep going and you just add them all up until you get to the mth term. Okay, so the K here is what we call a dummy variable. Okay, that really doesn't matter. It's okay. It's also called a couple other things. What do they call it? It's called the index of summation, or the summation variable, or you could just call it the index. Okay, and it really, and by dummy I mean it doesn't matter what symbol you use. It doesn't need to be K. Okay, I could have written the same thing and said instead of K I could have used a, oh, I don't know, how about a J? And it means exactly the same thing. It means that this J is going to start here at 1, and we're going to go using natural numbers or integers and go 1, 2, 3, 4 all the way up to M, and you get exactly the same thing. The symbol you use for the index does not matter. Okay? Now, I'm going to let's make this a bit more concrete. So, for instance, actually, not quite concrete yet. Let's say we have the sum, and this is how you would read this. The sum, as n goes from 0 up to 3, of some sequence Bn would be, now, well, let's think about it. It's going to be B something plus, 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 plus a bunch of B somethings. The index starts here at 0, which, yes, it could start at 0. Now, I know we talked a good deal about how in this book they use that sequences are always going to start at 1. We're basically going to completely throw that out now. Like, it could be anything. It could be a negative number. It could be a lot of different things. But it's always integers, right? It's always whole number amounts that we're ranging through with n. So here, n is going to start at 0, and so we just plug that in for that number right there. Okay? So Bn begins at 0. Then you add that to, you increase it by 1, and so it goes B1. Then it goes up to B2. Then you add that to B3, and that's where you stop. You're including these endpoints here. You see the 0 shows up. You see the 3 shows up. So then how many terms are here? Well, that's something to notice here, right? Since you're counting the 0 and you're counting the 3, you end up with one more than the difference between these two things. Like, you might say, well, it's kind of like when you have, numbers. Like, let's say that I say, do numbers 1 through 5, and forget about the odd. How many problems am I doing for homework? Well, you'd think, well, 5 minus 1 is 4, so I'm doing 4. No, because you're including the 1, right? Same thing here, you're including the 0. So you don't go 3 minus 0 is 3. You think, well, the total number of terms that I have includes the 0. And so I have 1, 2, 3, 4 of them total. I'm not just saying, this is going to come into play later. Now, just so we don't get it in our heads that, like, well, we'll just do one more here. Try this. I want you to pause the video and tell me what you think. What do you think this means? Pause the video right now and write this thing out. Okay, what you should have gotten is by the same logic here, and here we're taking f as some function of j, and we're just going to start here with 3, and then we add that to whatever we get when we plug in a 4, plus whatever we get when we plug in a 5, plus whatever we get when we plug in a 6, plus whatever we get when we plug in a 7, and we're stopping at 7. Again, the total number of terms here is 1, 2, 3, 4, 5. And you think 7 minus 3 is 4. But you're including the endpoint. So it's not just the difference, right? The total number of these is that minus that plus 1, 5. But anyway, we'll talk about that in a second. So that's all there is. Just note, they don't always start at 1, okay? There may be a very good reason why you want to start here at 3. There may be a good reason why you want to go to 0. Another thing, they could, these things, let's use n, and you have some a sub n, they could go all the way up to infinity and all the way down to negative infinity. Now, you won't see this negative infinity here for a long time, but soon enough in this chapter we'll be talking about what happens when you have a sum that goes all the way out to infinity. Interesting stuff. So just so you know, right, you're not going to see it in your homework. These can take on negative values. That's perfectly fine. It could take on the value 0. It could go all the way down to negative infinity. So just so you know, all right? So let's do some concrete examples here. All right. So for these, we are going to find the sum. And what that means, I think that's what your book says, find the sum. And that means to evaluate. Evaluate the sum. Right, sum is just plussing a bunch of things together, right? So we're going to actually evaluate what this stuff means. So here's an example. Here's number 34. It tells you to evaluate this sum right here. K goes from 1 to 6 of, what are we doing? 10 minus 3k. Pause the video and try to figure this out. Okay? So this is your formula. This is kind of like your sequence, 10 minus 3k right here. And if I gave you that and said, write the first 4 terms of the sequence, you would just say, well, when k equals 1, when k equals 2, and then you just do that. That was your homework last time, right? Same thing here. Here's a formula for finding a sequence. Now, instead of putting commas between each of the things in the sequence, we're just putting pluses in between them. That's all there is to it, right? So we do that. When k is equal to 1, we have 10 minus 3 times 1 plus 10 minus 3k is equal to 2. You see, each one of these things, kind of what goes through my mind as I do this. Actually, let me give myself a bit more room here. Sorry about that. We're going to say it was the sum as k goes from 1 to 6 of 10 minus 3k. The first one is 10 minus 3 times 1 plus 10 minus 3 times 2, and so on. And what I was saying is what goes through my mind is something like this. Right? The first thing you get is when k is equal to 1. The next thing you get is when k is equal to 2. The next one you get is when k is equal to 3. And so I plug in a 10, 3 times 3, like that, plus, the next thing I get is when k is equal to 4. And so I go 10 minus 3 times 4, plus, this is when k is equal to 5, and so we have 10 minus 3 times 5. Finally, sorry, this is going to look really ugly. This is when k is equal to 6. We get 10 minus 3 times 6. Now let's actually evaluate it, right? Like, yes, this is true. That's nice. But we can actually figure out what this is. So let's do this. 10 minus 3 times 1 is 10 minus 3 should be 7. Plus 10 minus 3 times 2 is 6. 10 minus 6 is 4. Plus 10 minus 3 times 3 is 10 minus 9 is 1. Plus 10 minus 3 times 4 is 10 minus 12. That's negative 2. Okay. Looks like we have some abusive notation here. Plus, minus, that's just minus, right? Okay, so plus 10 minus 3 times 5 is 10 minus 15. That should be minus 5. 10 minus 3 times 6 is 10 minus 18, which is minus 8. If you noticed, I had to look at my notes to make sure that was, I can't do that in my head. Okay, so now we just have 7 plus 4 plus 1 minus 2 minus 5 minus 8. That's the same thing as 12 minus 15 should come out to negative 3. So all that right there, as you can see, that nifty, that cool looking thing, and now when like you watch a TV show or a movie and like there's some mathematicians doing stuff, if you happen to watch movies where mathematicians do stuff, if you're like me, then when you see something like this, you know, now you know what it means, right? This is all it says. Just plug that in, plug this in where k equals 1 all the way up to 6, and then just add all of them together. And now what you get is that that thing, that symbol right there, is equal to the number negative 3. Let's do another one. This is number 38. Now your book has this as k being the index, but like I said, the index does not matter. It's a dummy variable. It could be anything. So I'm going to change it to n, because that's I feel like doing that. n minus 1 times n minus 3. Okay? Pause the video. Try to figure out what that is. Okay, that's, you plug in a 0 first. So we get 0 minus 1 is negative 1. 0 minus 3 is negative 3. Add that 2. Now we're plugging in and n equals 1. 1 minus 1 is 0. 1 minus that, blah, blah, blah. 1 minus 3 is negative 2. Plus. And again, I almost lost track of myself. I forgot that I was here at 1. So here's when n equals 0. N equals 1. Now when n equals 2, this expression becomes 2 minus 1 is 1. 2 minus 3 is negative 1. Add that 2. What do we get when n is equal to 3? 3 minus 1 is 2. 3 minus 3 is 0. Plus n equals 4. Now we have 4 minus 1 is 3. 4 minus 3 is 1. I think that's what I got here. Let's see. A 1, 0, and 2. 1, and 1, 2, 0. Yep, okay, did it right. So now, we're just going to go through and evaluate these. The negatives cancel. 0, stop thinking about it. Plus a negative 1 is negative 1. Plus a 0 is 0. Plus 3 times 1 is 3. So we have 3 minus 1 plus 3. Is that what I got here? Yep, 3 minus 1 plus 3. Same thing as 6 minus 1 should be 5. There's your answer. Okay, one more. Same prompt, find the sum. We're going number 44. It says to find the sum. And I changed it here to J, as J goes from 1 to 1,000, of 5. Pause the video and see if you can figure this out. So, before, right, when we had the sequence 5, right, we said, well, it's basically like a constant function. No matter what number you plug in for n, then the output's always 5. So this is just 5, 5, 5. This is no different, right? This is like you have some function of j, right? J is the input variable. And instead of it showing up in here like it might have, or like it did with the previous ones, right? Where like j minus 1 times j plus 2 or whatever, right? Well, it doesn't show up, so that means it's just the constant output of 5. Okay, so this is just 5 plus 5 plus 5. Okay, so let's think about this. It's 5 plus 5 plus, and so on until j equals 1,000. So this is when j equals 1. This is when j equals 2. And so on all the way up to j equals 1,000. So the question is, how many 5s do I have? This is easy in this case because you're actually including from one, you're including one and you're going all the way to 1,000. It might be easier to see if you're saying how many of these are there if j starts at 1 and goes up to 5. Well, you'd say, well, j equals 1 is the first one, j equals 2 is the second, and everything has its own name. There's a total of 5 of them. And so this is easy whenever you're starting at 1. You have a total of 1,000 of these things. And if you know that you have, so this is a total number of 1,000 fives, which we could rewrite like this. I could pull a 5 out, right? There's a 5 in every single term, so I'm going to factor it out, leaving me a 1 plus all the way up to the 1,000th one. So there's, right here, there's 1,000 ones. What's 1 plus 1 plus 1? 1,000 times. Oh, it's just 1,000. Nice. Okay, so that's 5 times 1,000, which is just 5,000. Not that bad, actually. Here's a question. Try this one. Pause it, see if you can figure that one out. Okay. That's the same thing. It's just 5 plus 5 plus da 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 da. But now how many of them do we have? Well, when it went to 1, we had a total of 1,000. Now we're just adding one extra one, right? So before it was j equals 1, j equals 2, j equals 3, all the way up to j equals 1,000. This is 1,000 of them. Now you're just adding one extra one on. You're adding in when j is equal to 0. And so you have one more. All together, you should have 1,001 fives. Which means that if you factor out the 5, you have 1,001 ones. 1,001 ones, all added. That sounds terrible. That many ones all added together gives you 1,001. Which should give you what, 5,005, I think? I didn't write this down. I went to look. I really did. I was like, it's 5,005, right? Oh, I didn't do this one. Yeah, but that's the, yeah. So, okay, that's what I was saying. It's kind of important to keep in mind how many of these things you have. Where you start is going to depend on how many of them you have. That's going to change your answer, okay? Okay, now this leads us right into this nifty thing to notice, because you could have said, well, it would have been true no matter what constant number I had. If I have a 5, and so you end up with a 5 that you pull out of here. But if I'd had, a pi, right? If I had pi, I'd have pi plus pi plus pi, and then I could pull a pi out of every one of them. And so this leads us to something that we could generalize now. So, theorem. And we're going to call this sums of a constant. Sums of a constant. So these are two theorems on the sums of a constant. The first theorem is that the sum as k goes from 1 up to n of some constant c. So let's go ahead and put this up here. C is any real number. Actually, this is still true if c is any complex number. So it could be, that could be 7 plus 3i. And what we're about to do will still be true. And since the reals are a subset of the complexes, right? The reals are a subset of the complexes. Then if you use a real number, it's still true. But what's a subset of the reals? Well, all of the rational numbers, all the quotients, right? So it's true if that's a rational number. What's the subset of that? Well, all the integers, they're a subset. And so basically what I'm saying is that it's just trying to say this as broadly as possible. This is true for any complex number. And therefore it's going to be true if that complex number happens to be real, if that complex number happens to be pure rational, if it happens to be an integer, no matter what, if that's a constant number, my claim is that this is equal to n times c. So we're taking the sum from 1 up to n. Okay, so let's prove this real quick. It's not hard, right? In fact, why don't you pause the video and prove this? Okay. Well, what does this say? This says you go, okay, this says just take c and go plus c plus and so on. How many times? Well, you're doing this when k is equal to 1. You're doing this when k is equal to 2. And you keep doing that until k is equal to n. How many of these do you have? Well, like we just said, right? It's a total of n of them. And so you factor out the c, and you have 1 plus 1 plus all the way up to 1. And there's a total of n of these. There's n ones. Well, 1 plus 1 plus 1, a total of n times, is c times n, which proves the statement. Okay? Okay. Here's the second one. The sum as k goes from m up to n of some constant is equal to n minus m plus 1 times c. Now this is why I was harping on this earlier, so this is not coming as a surprise to you. So let's just prove this. Okay, you have k equals m up to n of c. C does not change no matter what k is, so when k is equal to m, you get a c. You add that to when k is equal to m plus 1, you get a c. All the way up until you finally get to n. And k is equal to n. Now we're asking how many of these things are there? Remember, it's the same kind of thing as before. You can't just say it's n minus m. Right? Because if we tried that earlier, right, when that was 1, you would say, well, it's n minus 1. You have a total of n minus 1 things. But that's not the case. That wasn't the case here. You have a total of n things because you have to count that first guy. Right? When you subtract, you miss. When you take n minus 1, you're missing that first guy. And so if we take n minus m, it's like you're forgetting about all of these guys. So I just want to make this very clear here. Right? Let's say that when k equals 3, k equals 4, k equals 5, and k equals 6. So we have this sum as k goes from 3 up to 6. If you just say 6 minus 3, 6 minus 3, it leaves that guy off, right? 6 minus 3 is 3 things, and there's your 3 things, but you're forgetting the first bit. You can't subtract him off. So you need to add him back in. And so we'd have 6 minus 3, but then you add in the one that you're missing. And that would give you the correct number. 6 minus 3 is 3, plus 1 is 4. You have a total of 4 things. Same thing's going on here, right? You're going to say, well, how many things do you have here? Well, n minus m leaves him off, so let's count him by going plus 1. So that's how many c's you have here. You have n minus m plus 1 c's. So you have, factoring him out, you have plus 1, plus 1, plus 1. How many of them? Well, there's n minus m plus 1 ones, which is c times n minus m plus 1. Okay? So that's where that comes from. That's why, and it looks really weird. When I look at that, I'm like, what did we do wrong? Like, every time I see that, I'm like, that can't be right. But it is. Okay, you take the biggest one minus the smallest one, but doing that forgets the first one, so you have to add him back in, and that's where that plus 1 comes from. Okay, so here's an example of how you're going to use that. This is number 46. This is the same thing. It's still just evaluate, right? Evaluate the sum. Okay, and here's the sum. N equals 137 up to 428 of 2.1. Do this on your own. Okay, so we know that it's, I'm gonna do it the hard way. 2 plus 1, 2 plus 1 plus 2 plus 1 for each one of these, right? Starting at 137 up to 4. So then the question is, I'm going to factor out a 2.1, and we have a 1 plus and so on. Now we just need to figure out how many 1s do we have. Well, it's that minus that plus 1. So 428 minus 137 gives you, notice I'm looking at my notes, 291. But that's not all. We'd be forgetting that first guy, and so we have to add 1, and so we should have a total of 292 ones right there. So that's 2.1 times 292, which, if you work it out, I think I did this right, 613.2 is what I got. If you got something different, let me know. That would be interesting. So, there you go. Now we're going to talk about partial sums. Partial. I think I spelled that right. Partial sums. Okay, so in calculus, and also later this chapter, like I said earlier, we're going to encounter sums that look like this. The sum as k goes from 1, or really any number, but usually 1, or 0 actually is. Later in this chapter, we'll be starting at 0 a lot. And if we're not, you're going to want to start at 0. But anyway, sorry. The sum as k goes from 1 up to infinity of a sub k. Right, now does this make any sense? Well, think about what this a sub k, remember this a sub k here is a sequence. And last time we talked about infinite sequences. This is just A1, A2, A3, and so on, up to AN. And we keep going on and on and on forever. We've already defined that as a thing. Now what we're going to do is take those and add them all up. Sometimes you get something useful. You actually get a number that actually converges to a specific value. Sometimes it just blows up. Like, for instance, if this were a constant, right? Like if this were the sum as k goes from 1 to infinity of 5, you'd have 5 plus forever. Obviously that's junk. That's infinity. It doesn't converge to a finite number. It gets as large as you want. You give me any number. A billion, trillion, raised to the billion, trillionth power. Eventually this will get bigger than that. So it's like, yeah, yeah. But there are times where that doesn't happen. There are times where if you add up infinitely many things, it actually converges to a number. And one of the ways that we get a grip on this is to take a partial sum. So instead of adding this thing all the way up to infinity, adding up all infinitely many of them, we chop it off at some point. And we look at the first however many terms. Let's say n. We look at the first n terms here, and we get 1, a2, plus all the way up to a sub n. And then in practice, like in calculus, what you'll do is you'll look at this and say, well, what happens as we make n get bigger? Like, maybe we could get some kind of formula here. Maybe we have you could figure out, okay, this is some function of n, and then we look at what happens when n gets really, really, really big. Does this thing blow up? Does it shrink down to a smaller number? Does it converge to a number? And that's why they're introducing this, so that when this is why I want to introduce this now, so that when we go to see this in calculus, we don't have to learn all of this stuff at one time. While we're trying to learn the theoretical calculus on top of it, we could already have this in our pocket, right? So, or in our toolbox, is what I mean to say. And so, in order to get a handle on this guy, where you're adding up infinitely many things, sometimes it's nice to chop it off and take a look at the partial sum. And what's very standard is to use a capital S to denote this right here. Your book does that. And so this is what we call the nth partial sum of the sequence a sub n, or a sub, I don't want to say, because since we're using n here, I want to try to say that, a sub k, okay? It doesn't matter. If you know what I'm talking about, I don't, you know, we're not going to worry about that. But this is the nth partial sum of this sequence, this given sequence. Okay, and so, like I said, like what you'll do in calculus is you'll compute this thing, see what it is, and then you'll take a look at what happens as n gets really, really, really large. And that's actually what this means. That's how that's defined. You can't plug in an infinity, right? That's what this means, is you take the nth partial sum, and then you look at what happens when n gets larger and larger and larger. What happens to this thing? Okay? Now, there's a lot of reasons, not just like in calc, but there's a lot of reasons why this thing is very useful. It often shows up in proofs. Yeah, and so, okay, check this out. So, given a sequence, say a sub k, I give you some sequence. Maybe I give you a formula for it, right? Maybe it's 1 over n squared plus root n over n cubed. I don't know what, I'm just making this up, right? You have some sequence, I give you a sequence. Now, given that sequence, now what we could do is construct a new sequence. And that would be the sequence of partial sums. Ooh. Oh boy. And then we could ask the question, and this is kind of what I've been hinting at here, is then you ask the question is, does this sequence converge? Again, in this class, we're not worried about convergence. So you don't need to be like, well, how do I figure that out? You'll get there, don't worry. But this is technically how it's done. Really, you just compute this thing and see what happens to n, but technically, the definition for all that to work, remember how I said real numbers were defined? They were defined in terms of sequences, like that a real number is a sequence, is all the sequences that converge to this thing. Well, if you can, in order to really get down to the nitty-gritty of something, it makes your life easier if you could put it in terms of a sequence. So this really bugged me at first when I'm like, why don't you just look at this thing and then just make n really big? Like, why would you need to talk about this? Well, technically, this is what you need in order to have a very fully rigorous proof of something. So this is far beyond where we need to go. And in fact, if you just take calculus and advanced calculus, this will probably never come up again. But this is a big thing in analysis, which is like the rigorous footing, the rigorous foundation for calculus. If you go into analysis, this is something you're going to talk about, and I just want to kind of introduce it here. But your book also harps on this, and you're like, who cares? Like, why? Well, this is why, because there's some real theoretical underpinning to this stuff, and this is how you deal with these things. And so if you want to figure out whether this thing converges, technically what you're doing is you're asking, does this sequence of partial sums converge? And let's kind of demystify this a little bit, because what is, so here, I'm going to get rid of this. S sub 1, the way I just defined it, that's just the first partial sum. So that's the sum as k goes from 1 up to 1 of the ak's. Well, that's just a1. So this thing is just a1. Okay, well, what's s2? Well, I change this to a 2. I change this to a 2. And now it says go from 1 up to 2. And so a plus 1, a plus 2. Okay, so this second one here is a1 plus a2. And guess what the third one is? Yeah, that's right. It's, you just should change that, and now you're adding. You'll notice that this one, the only thing that changes each time is you're just adding one extra term onto here, right? And so, well, that'll be nifty if you go to compute these things. You'll have to compute these things. So it's just something to notice, right? That's all that's going on here, right? And you go all the way up to, let's say, s of n. The nth sum is just a1 plus a2, all the way up to an. The next one would be the same thing, but then you're just adding on an n plus 1 at the end, right? And so on and so forth. Okay? So again, this is called this is called the sequence of partial sums. Okay, that's the name of this thing. So again, given any sequence, you can compute its sequence of partial sums. So let's do it! Number 30, it says, find the first 4 terms of the sequence of partial sums of the given sequence. So what's the given sequence? Well, in this case, they give you this sequence, 1 over n squared. And what we want is S1, S2, S3, and S4. So, okay, let's just do this. S1, by definition, is you just take k, as k goes from 1 up to 1 of this thing, 1 over k squared. Ooh, notice what I did? It's like, oh, but that's an n. Yeah, I used a dummy variable, right? That would be like we're doing something, I have some f of x equals root x plus 1 over x. And I say I graph this thing. But then I go ahead and I say, okay, well, I'm going to graph it on the t-axis because maybe I'm thinking about this in terms of time. And so I don't graph the x, I graph the t. I'm graphing f of t. It's the same thing, right? Same thing, that's a dummy variable. It doesn't matter what name you give it, right? It doesn't need to be an n, it's a k, whatever. If you like, if that really bugs you, you could just say, here's your n. And it's the exact same thing, okay? So I wanted to do that deliberately. But really, like I said, it's a dummy variable. Doesn't matter what you use as long as the definition matches up. That's a function right there. That is a function. Right? Remember how we define sequence. So it doesn't matter what symbol you use to denote it. But we'll use n. Why not? So the first one is, well, when n equals 1, I plug that in, I get 1 squared. That's just 1. Okay, so that's 1. Easy. Okay, now S2 is defined to be as n goes from 1 up to 2 of 1 over n squared, which is, well, when n equals 1, we get 1 over 1 squared, plus when n equals 2, we get 1 over 2 squared. Okay, so that's 1 plus a quarter, that's 1.25. Okay, nice. Now, S3, n goes from 1 up to 3, 1 over n squared is, I'm going to go ahead and write it out. But I think you know there's a much easier way of dealing with this, right? I could say, okay, when n equals 1, I go 1 squared. When n equals 2, I go 2 squared. When n equals 3, I go 3 squared. And I could go through and say, okay, that's the same as a quarter. That's the same as a ninth. And then I do a bunch of stuff, and I think I got this right. I didn't double check myself, and I did a really poor job. I got that. Could do it that way. Or you could say, well, here's, we know S3 is the same thing as, isn't that just S2? Then then just add it to whatever the third term was, which happened to be that. Right? Like thinking about this is just your A1. This is just your A1 plus A2. This is just your A1 plus A2, which is the previous one, but then you're just adding on A3. So you could do, I really don't care as long as you like find all 4 terms here, right? That works out like that. You could have done this instead of saying, well, we just computed that. I know it was 1.25. And if you want, I'm not going to be a stickler. If you want, you could go ahead and turn this into decimals. Find 1 over 9 is, what is it? Yeah, so 0.1. Okay, yeah. So you go 1.25 plus 0.1111 repeating is 1.3611 repeating. That's fine too, right? And so then when you go to compute S4, you get the sum as n goes from 1 up to 4 of 1 over n squared, which is the same thing as S3, the previous one, plus the last one, which is going to be 1 over 4 squared, which is going to be 1.3611 repeating, plus 1 over 4 squared is 1 over 16, which is whatever that is. You convert that to decimals and blah, 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 blah. Okay? So that's fine. I really don't care if for these right here you use a calculator and just do decimals. That's fine. That's fine. That's cool. Okay, a couple more things to cover here. More theorems on sums. Now, for each of these, we're going to suppose that if A1, A2, and so forth, right? So obviously that's a sequence. If the sequence A1, A2, and so forth, and B1, B2, and so forth. So two sequences, A1, blah, 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 blah. Maybe it's 1, 1/2, 1/4, and so forth. And maybe B1, oh, excuse me, maybe B1 is 2, 3/2, 4/3, and so forth, whatever. Any two sequences, don't care which ones they are. So if A and B are infinite sequences, okay, as defined last time, you take any two infinite sequences, okay, so that's we're supposing that's true. Okay, so if you have two infinite sequences, then for every positive integer, positive integer n, so you give me any positive integer, 1,000,000, 3, pi, oh wait, pi's not an integer. You see why we can't have pi. This has to be a positive integer. For every positive integer, then the following things are true. 1. The sum as k goes from 1 up to n. See why it has to be a positive integer? Yeah. 1 up to n of ak plus bk is equal to, can you guess? The sum as k goes from 1 to n of the ak's plus the sum as k goes from 1 up to n of the bk's. Okay? Now let's prove this. Alright? Starting with the left-hand side, we have the sum as k goes from 1 up to n of akbk is equal to, well, just by definition, we have a1 plus b1 plus a2 plus b2 plus all the way up to an plus bn. Well, those parentheses don't matter because we're just adding stuff together. There's nothing multiplied on the outside. Okay, so I could drop all the parentheses. A1 plus B1 plus A2 plus B2 plus all the way up to AN plus BN. But this is just a sum, right? I mean, like we're calling it, now you hear the word sum and you're like, oh, this crazy looking thing. Well, no. Like, you're just adding up numbers. You're just adding up numbers. It doesn't matter. So we could rearrange these numbers. How about we arrange it? So A1 plus A2 plus all the way up to the AN. And now we'll rearrange all of these to get the B1 plus B2 plus all the way up to the BN. All right, that's legit, right? I could do that with a sum. You'll still get the same thing if you ordered it differently. But what is this? Well, by definition, that is the sum as k goes from 1 up to n of the ak's. This, right here, is the same thing. This is just a fancy way of writing this. We'll write it in the fancy way. K goes from 1 up to n of the bk's. Just a fancy way of writing this, okay? That's all that is. And whenever you see this, your mind should immediately see this right here. When somebody gives you this, you should immediately see in your head that thing happening, okay? So when I see this, what goes through my mind isn't that, it's this. And trust me, that's to your benefit for the future. You want to have that in your head, okay? So this is proved. Okay, so we got statement 1. Statement number 2 says that the sum as k goes from 1 to n of ak minus bk is equal to, take a guess. Guess what it's going to be. I'll give you a hint. It starts off like this. K equals 1 up to n of the AKs. Minus, yes, the sum. This K goes from 1 up to n of the BKs. Now, you have to prove this for homework, okay? It should look very similar to what we did here for number 1. It should look almost exactly the same. There's going to be some minor differences somewhere, but you should be able to figure that out, okay? I'm not going to say anything else. You should be able to do that. You should be able to do it well. I expect it to be done well, okay? All right, and finally, the third one is the sum as k goes from 1 to n of c times ak. And here, I'll just go ahead and put over here where c is, yeah, c is any real number. Or honestly, like, it does work with complex numbers. It does work with complex numbers. It's still true when you let your constant be a complex number. Just something to know. Works for complex numbers, but anyway, constant though, okay? That can't change. That cannot vary. That cannot be a formula involving k. Like if I say that my c is like 2k plus 1, no, that's not a constant. It has to be a constant number, like 5. Or 3 plus 7i, right? Something like that, a constant. So I do want to keep this up here where c is any, we'll just say complex number. And you should know that we're talking about real numbers in this class, blah, 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 but it's true for any complex number. Can you guess what it is? The sum is k goes from 1 to n, ak times that constant. Okay, I'm going to erase all this so that I can prove this one right here. All right, but these are the theorems on sums. Memorize, put in your mind forever. Okay, so let's prove statement number 3. We start on the left-hand side and say, okay, suppose that we have the sum from k goes from 1 to n of some constant times this. Okay, now let's make this a little bit concrete. Let's say that my AK is like, I don't know, 2k plus 1 over 3k, something like that. Okay, now then C times that would be something like, I don't know, 5 times AK, which, you know, you could write it like this, 5 times 2k plus 1 over 3k. Or maybe it's distributed through, right? Maybe it's 10k plus 5. So the cool thing here, the thing I'm trying to show you is like, even if this was your AK, let's say that your AK was given like this. Since we can factor it out, we can factor out a 5. We could rewrite this like this, 2k plus 1 over 3k. Then this theorem's still going to apply. It's just that, like, here's the part that's moving, here's the moving part, the part that changes with k. You could pull out a constant. So all this says is if you have some expression where you basically have your function of k right there, and you could pull out the stuff that doesn't change every time, then what you get is, and you've seen the conclusion, you've seen the other side of the equation. But it's just something to note, okay? So let's prove this. What is this? Well, by definition, this just says take whatever is there, and then you just vary. When k equals 1, we get a 1. And you add that to c times whatever you get when you plug in a 2, plus, and so forth, all the way up to c times whatever it is when you plug in a n. Well, let's just factor out that c. The c is the same. In every single one of these, you have exactly one c, and you can just pull it out. Right? A1 plus A2 all the way up to AN. What's that? Well, by definition, right? That's what that is. Then we just have a fancy way of writing it. It's just the sum as k goes from 1 to n. As k starts at 1, goes all the way up to n. So yeah, I got that right. Of my AKs right there, and that's that simple, right? And let's do an actual example like that. Like for instance, let's say that my AK was, I'm going to make something simple here, 2k plus 1. Okay, what would that say? Well, let's say that my C is like 5. Okay, well this would say you just take, and let's not go forever, let's say 3. Okay. Okay, plug in a 1. We have 5 times 2 times 1 plus 1 plus 5 times 2 times 2 plus 1 plus 5 times 2 times 3 plus 1. And you could see that's the same thing as this. Just pull out that 5, and you have 2 times 1 plus 1 plus 2 times 2 plus 1 plus 2 times 3 plus 1. Yeah? Yeah, that works, right? And isn't that the same thing that you would have gotten if I told you, hey, write this in summation notation? You could say, well, it's the thing that changes. It starts at 1, and so that's the thing. It starts at 1, it goes 2, it goes 3, and that's it. So you'd say it goes 1, 2, 3. Let's give it a name. Oh, how about k? Okay, so k. And so what is it? This thing is changing each time. It would be 2k plus 1. That would be the thing that you're doing. Yeah, and that is the same thing as that. Yeah. Okay, so that's basically that third statement means that you can pull out constants from sum, which you've known for years and years now. It's worth saying because now we have this weird, funky looking notation, and we do want to make sure that it does behave the way that we expect it to behave, which it does. So that's nice. K goes from 1 up to, let's just start with 3. Of what? How about K? Pause the video, write this out, tell me what it is. You should have gotten 1 plus 2 plus 3. Alright, which is 2 plus 3, okay, that should be 6. Okay, let's get the next one. See what I'm doing here. K going from 1 to 4 of K is 1 plus 2 plus 3 plus 4, which of course is the 6 plus 4 should be 10. Let's do that another way to make sure. That's 7, 8, 9, 10, yes. Okay, that looks good. Okay, so, yeah, I'm going to do this guy down here. Let's say K goes from 1 up to N of K. Well, what's that? You should be able to write this out in expanded form. This is what we call this. There's your summation notation. It can be rewritten in expanded form as 1 plus 2 plus 3 all the way up to, well, N. That's all that is, right? You'll notice basically what I've done is I've computed the partial sums of this partial sum. Sorry, I probably should have introduced this a little bit differently, but this right here is a partial sum. I think it's pretty obvious that this thing cannot go on and on forever. it's just going to get bigger and bigger. It's not going to converge as we make n smaller, right? But here's the thing. It will be very, very useful now and in the future to have a formula for this. And if you just kept computing these, let's go k equals 1 up to, say, 5 of k. Well, that's 1 plus 2 plus 3 plus 4 plus 5, which should be 15. It's not easy to see a formula here, right? A difference of 4 there, a difference of 5 there. Maybe it's a difference of 6 the next time, but and how do I write that as a formula? Kind of hard. There is this really cool trick, and this is what I want to show you. So first off, this was S3, yeah? This was the partial sum 3. This was the partial sum for the partial sum 5, right? So I'm gonna go, I want these on the board because we can see clearly, yes, that is that. That is that. This is this. The fifth partial sum, the fourth partial sum, and the third partial sum. Now what I want to do, because I'm going to use that to check this formula that I'm about to derive. I'm going to derive this formula. So first off, S sub n, the nth partial sum, is just 1 plus 2 plus 3 plus all the way up to, well, n minus 2, n minus 1. Finally it ends at n. Yeah? Yeah, sometimes it's nice to include some of these in your work. So, okay, everybody buy that, right? That should work. If we're going up to 10, then that would be 9, because 10 minus 1 is 9. 10 minus 2 is 8, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Okay. Okay, there's that. But I could rewrite that. I'm just going to reverse the order. Okay, I'm going to start with n right here. Then I'm going to add the n minus 1 right here, n minus 1. I'm going to add the n minus 2 right here. And I keep flipping. I'm going to flip all these guys over. And then finally, the last 3 would be 3, 2, and 1. So I'm going to have my 3, my 2, and my 1 right there. Everybody buy that? That you could write a sum in the reverse order and it's the same thing. Okay, good. Now I'm going to do this. I'm just going to add them together. X plus x is 2x, right? So Sn plus Sn should be 2 Sns. Yeah? Right? Okay. Now, let's do this. 1 plus n is n plus 1. Okay. Plus 2 plus n minus 1. Let's see. N minus 1 plus 2 is the same thing as n plus 1. Okay, so we get another n plus 1. N minus 2 plus 3. N minus 2 plus 3 is, what do you know? It's n plus 1. Okay, so plus n plus 1. Right. All the way up to, oh hey, I just saw that, right? N plus 2 plus 3 is n plus 1. 2 and n plus 1, that's n plus 1. That's n plus 1. Ah! I have n plus 1 plus n plus 1 plus n plus 1 plus n plus... It's the same term every single time. It means I can factor it out. So let's factor it out. I have n plus 1. I'm going to factor it out. And now all that's left is 1, 1, 1, 1. So I have 1 plus 1 plus... Question. How many 1s do I have now? Should be 1 for every single one of these, right? We had the same number of terms in each thing here, and so that should be the same number as those, which should be n, right? Because we are including 1, and we're including n, we're including the endpoint, so it should be n of them. So this is n plus 1, 1 plus 1 plus n times should just be n. And so we have 2 times the sum n. Should give me that Sn is n plus 1 times n. And I have to write it that way. I'm sorry to reverse it right here, but I have to write it this way. I can't bring myself to write it this way. I have to put the n first. And then there, right there. Now, let's just check it. So S3, using this formula right here, S3, formula tells me it's 3 times 3 plus 1 is 4 divided by 2, right? Check that, right? The same number shows up there, yeah, and then it's 1 more than the previous, yeah. And so 4 divided by 2 is 2, so we have 3 times 2 on the top, which is 6. Nice! Let's try it with 4. The fourth partial sum, this tells me, is 4 times the next one is 5, all over 2, which is 2, and that 2 times 5 is 10. That's what we got. Nice! Let's do the other one. S sub 5, formula tells me it's 5 times the next one is 6 over 2. 6 and 2, that divides, and it gives me 3. 15. Nice. Okay, I wanted to bring this up because this will be very useful in the near future. And this is, now we can consider this proved, okay? The nth partial sum of the integers, the positive integers, 1 plus 2 plus 3 plus all the way up to n, is n times n plus 1 over 2. We consider that proved. We're done. Like, this is true. It's obviously true. I did not need to go through and verify this to show that it was true, because I showed that it was true right here with this, okay? But this will be very useful in the future. So I'm going to go ahead and take care of this right now. That's all I got. Take care.